jointed frames, so that is trusses using stiffness method. So stiffness method again, and it's the third kind of structure. First we discuss the beam analysis with the help of this stiffness method, then the rigid joint frames, and now the pin joint frames we are discussing. In pin joint frames, what happens, we ignore the surface of the elements, and then the pin joints, we consider them as a fractionless, so we assume that it is not going to resist any moment. Moment resisting capacity is 0. And when we assume this, so the fixed end member and actions, that will become equal to 0. So by saying this, in equilibrium equation, if you see, the ADL matrix is going to be equal to 0. And then the AML matrix is going to be 0. So its matrices solution will be rather easy as compared to the beam one and that of the rigid joint frames one. So starting now from the lecture, now topics to be covered in this module will include introduction, prerequisites for using stiffness method for trusses, kinematic indeterminacy of trusses, stiffness method procedure for truss analysis, procedure of computing stiffness matrix in local and global coordinates, analysis of trusses, and we will discuss 4 problems, problem 1, 2, 3, and 4. Introduction. Now, because of 3 reasons, we want to analyze these trusses with the help of stiffness method. First reason is that it is more systematic. We can compute reactions at all the supports, and then internal resisting axial forces in any member of the indeterminate truss can be found. It will be having only axial forces along the axis of the member. It can be tension, it can be compression. Now, the basic method for the analysis of indeterminate truss by stiffness method is similar to the indeterminate beam and rigid frame analysis discussed in the previous lessons. However, fixed end actions are not taken in order to have simplicity in the structural model. Why? Because its effects are going to be negligible. Determine the degree of kinematic indeterminacy of the structure and then analyze the structure. So again, it's a stiffness method. So kinematic indeterminacy, which is the degree of freedom we will be looking for. And then we go and analyze the structure by following those now standard steps. Which one are the standard steps? The kinematic indeterminacy. Then the finding out the stiffness coefficient. ADL matrix is not going to be included here. So when we kinematic indeterminacy, we determine the unknown giant displacements corresponding to them. We identify the ADL matrix. So ADL matrix in step number 1 we found. And step number 2. Now ADL matrix is not there. So step number 2 will become finding the stiffness matrix now. And at that stage, while we are finding the stiffness matrix, remember the other values which we can find, those will be the AMD values. AML values are not going to be found. Why? Because the fixed end actions are 0. Third, then we apply the equilibrium equation. Equilibrium equation in this case will become AD is equal to S times D. ADL is not going to be there. So AD is equal to S times D. And similarly, the member and actions, it will reduce the member forces when we are finding out AM will be equal to AMD times D. AML is not going to be there. So it's a rather easy case as compared to the beams and this rigid joint frames. Now, prerequisites for the analysis, so it's the same which we discussed in case of the beams and rigid joint frames. You should be having enough concept of matrix algebra. Must be able to find the kinematic indeterminacy of trusses, and enough concept of the geometry is also, trigonometry is also important. Now, kinematic indeterminacy of trusses, how we find out? We will be discussing plane trusses, 2D trusses. So, regarding the 2D trusses, we will be discussing how we find out this kinematic indeterminacy. The truss is said to be kinematically indeterminate when the total number of degrees of freedom at joints exceed the number of reaction forces. Now, when there is a reaction, it means there is no freedom to displace. So, kinematic indeterminacy in that particular direction is becoming equal to 0. So, this is how it is phrased here. In 2D trusses, at each joint, there are 2 degrees of freedom. And which one are those 2 degrees of freedom? It is translation in the horizontal direction and translation in the vertical direction. But joints where supports are present reduce the degree of freedom according to their nature at the joint. Now, what will happen if we have a roller support? Roller support can restrain only perpendicular settlement to it, and hinge support can restrain both. So, restraint of the displacement is coming from where? It is coming from the capability of the reaction. If we take example of the hinge support, it can resist in the vertical direction, it can resist in the horizontal direction also. So horizontal and vertical displacements are going to be equal to 0. This means that we can write now a general equation to find out the kinematic indeterminacy, which is Ki is equal to 2J minus R. Now, J is the number of joints 2. From where this 2 is coming, these are the 2 possible displacements now, 2 possible degree of freedom, and minus reaction. So what we do, quickly we count the number of joints, we multiply that by 2. We assume like there is no reaction now. 2J means there is no reaction. But then when we look at the support conditions, when reactions are coming, so we deduct those from 2J, and we get the total kinematic indeterminacy of the pin jointed frame. So where J and R are number of joints and unknown reaction components respectively. So 2J minus R, this will give you the degree of freedom of the structure. Now, to illustrate this with help of the sketches now, we have this frame now. This is a truss, and find the kinematic indeterminacy of the truss. This is required now. If we look at A, B, C, D, E, and F, these are the 6 joints now. So J is equal to 6 is recorded here. And reactions, if we look at A, we have a hinge support. So 2 reactions are coming from here. And at D, again, we have a hinge support. So 2 reactions are coming from here. So R is equal to 2 plus 2, which is equal to 4. Now, equation already we have 2J minus R, so we plug in the values here, and 8 degrees indeterminate this structure is kinematically indeterminacy of this structure is 8 degrees. Now, which one are those 8 degrees now? At B joint, it's a free joint, so it can translate to the left, right, and it can translate up, down also. So horizontal and vertical displacement, 2 from B, similarly 2 from C, similarly 2 from E, and 2 from F also. So F you look at such kind of a structure, and in some cases, if you forget this equation by observation, you should be able to find out the kinematic indeterminacy of the structure, dealing with the nature of the joints and supports there. So next, now, if we look at this structure now, this is again a pin jointed frame. At the bottom, we have a hinge support. At the top, joint is free. At the left, we have a roller support which can slide up, down the screen. And then to the right, again, we have a roller support which can slide up, down the screen now. Now, this top joint, it is giving us 2 degrees of freedom to the horizontal and this upward. So horizontal and vertical. So we have 2 degrees from the top joint. From the right one, we have it can move in the vertical direction. So 1 degree of freedom from here, and from the left again, it can move in the vertical direction. So 1 from here also. The bottom one is not allowing any kind of displacement. So it means it is 4 degrees indeterminate problem. This was a kinematic indeterminacy by observation. If we apply the equation, so R is equal to 4. Which one are those 4 reactions? At the bottom, we have 2 reactions. To the right, we have 1 reaction. And to the left, we have 1 reaction. Number of joints. So you can see at these corners, all these 4 joints. The equation is 2J minus R. So 2 times 4 minus 4, it is equal to 4 degrees. So by observation as well as by using the equation, it is established that the structure is 4 degrees indeterminate. Now, coming to the analysis procedure, it's again the same steps which we did in case of the beams and rigid joint frames. So the basic method for the analysis of indeterminate trusses, kinematically indeterminate trusses by stiffness method is similar to the indeterminate beam and rigid frame analysis discussed in the previous lessons. However, fixed end actions are not taken in order to have simplicity in structural model. Now, the basic typical equation was AD is equal to ADL plus S times D. But in trusses, fixed end actions are equal to 0. So we put ADL equal to 0. And this equation now reduces to ADL is gone now. So AD is equal to S times D. Similarly, for member end actions, AM was equal to AML plus AMD times D. But in case of the pin jointed frame, now this AML is equal to 0. Remember, this AML was coming from the same sketches where we were finding this ADL matrix. So when we put this equal to 0, so this equation reduces to AM is equal to AMD times D. Now, computation of stiffness matrix. How we are going to compute the stiffness matrix. Now, remember, stiffness matrix, 2 kinds of stiffness matrices we have. One is in local coordinate system, and one is in the global coordinate system. Now, if I give you a simple geometrical problem where vectors are in the different directions now, they have different, let's say, orientations and directions. One is horizontal, one is at 30 degrees to the horizontal, to the positive axis, one is to the 60 degree, one is to 90 degree, and then maybe, let's say, 130 degree. And somebody is asking you that you add them up. So what we do, we resolve them into a general system. And what is that general global system? That is making their horizontal and vertical components. And then accordingly, when we find out vertical and horizontal component, then you can use the Pythagorean theorem or whatever to find out its result. So that is the basic thing. Now, if you take the example of the trusses now, what happens in trusses, like the one we were looking here in this truss now, if I take this BF member, let's say it is making 45 degrees, but if we look at this one, CE, it is now in different direction. This BC is in different direction. if we want to find out the resultant of these things, what is now the solution? Solution is we resolve them into its rectangular components, which are horizontal and vertical. So this horizontal and vertical, which is now same for all the members, that we call global coordinate system. And BF, let's say we take its x-axis along the length of this member in BF direction, and perpendicular to this we take its y-axis. So x-axis is along the length of the member, and perpendicular to that it is a y direction. That axis system is known as local axis system. It is local to this particular member. Similarly, for the CE member, what we do along its length, we take its x-axis, and then perpendicular to this, we take its y-axis. So that is the local axis system of this member CE. Similarly, if we take this CD, so along the length of this member, it is the local axis of this member, which is the global also for this member CD, and perpendicular to this, we take the y-axis of this CD member. So this is the description of the local axis system. Now remember, the local axis system, we will call this the member axis system also. And the global system, it is known as the structural axis system also, structural coordinate system. So we'll be discussing and developing the stiffness matrices now using these two concepts. Now, stiffness matrix in local coordinate system, which is for the member axis, and structural stiffness matrix in global coordinate system. So let's discuss this now. This is the same diagram which we discussed to find out it's almost the same. Why almost the same? Here used to be at this right corner, here it used to be a hinge support there, but it is a roller support here. Now these numbers, the green numbers, they are showing the member numbers now. Now we have a truss and global coordinate system as shown. What is the global coordinate? Now at the bottom you see this horizontal x-axis and the vertical y-axis. This is the global coordinate system. This D1, D2, D3 and D4, these are the joint displacements of this member 7, this orange member here, this diagonal member 7. So D, when it moves along the global x-axis, this D2, when it moves along the y, which is the global x-axis, so horizontal followed by the vertical. When we generate the stiffness matrix, so we will take first at a joint the horizontal displacement and then followed by the vertical displacement. Similarly here, at joint K now of this member 7, we have D3 and D4. D3 is the horizontal and D4 is the vertical. So horizontal and vertical, again, these are the global displacements. What will be its local displacements when we start pushing this now, or when we start stretching it along the length of the member now, along the local axis of this member? So that will become our D1. And for that D1, we will call DM1, because we need to now differentiate between this D1 and the member axis, which is DM displacement along the member axis now. So this will become DM1, and perpendicular to this, which is the y local y axis of this member, that will become our DM2. Similarly, at this joint K now of this member 7, along the length of this member, it will become DM3, and perpendicular to this, it will become DM4. So those are the displacements now. Now the locations, now we are taking this specific member 7 now, and we will be developing now the member forces and then the stiffness coefficients for this member 7. Member 7, what is the kinematic indeterminacy of this member 7? Again, it is 4 degrees. 2 degrees at joint J, which is D1 and D2, and 2 degrees at joint K, which is D3 and D4. Now coordinates of this joint and then the joint K, joint J and joint K, they are given. This J from the origin, it is located horizontally at XJ. Here we see it. And joint K, it is located horizontally at XK. So what is the horizontal projection of this member 7? It will become XK minus XJ, which is recorded here. Similarly, along the y-axis, the location of this J is Yj from the origin of this global coordinate system, and the location of this joint K, it is Yk here. So the vertical projection of this member 7, it is Yk minus Yj, which is recorded here. So this line should be at the top. Now, now we take this member 7 on the next slide. This is how we find out its coordinates. So now this is the same member 7 having length L, and it is making an angle theta with the horizontal. We want to develop these trigonometric equations now. Here, this green x-axis, if you look at, this is the local axis of this member, and this is the y local axis of this member 7. J and K are the joints, and here you see the coordinates, how they are located. This capital X and capital Y, these are the global coordinate system. So this is the x-axis and this is the y-axis. Now, cos theta from this diagram now will become equal to this base divided by hypotenuse. So base is xk minus xj, here we see it, and divided by this hypotenuse, it is L. So this is divided by L. So cos theta we can express in terms of the coordinates, which is xk minus xj divided by L. Similarly, the sine theta will become equal to perpendicular divided by hypotenuse. So perpendicular, it is given here yk minus yj and divided by L. So onwards, we can relate this theta to the coordinates. If we find out the coordinates, so we can replace the cos theta and sine theta with help of those coordinates. Here you see the local axis, and here you see the global system. And from now onwards, cos theta, we can use xk minus xj divided by L, and sine theta is equal to yk minus yj divided by L. Now here we see now displacements in the local coordinate system and displacements in the global coordinate system. At joint J, now at joint J, this D1 and D2, which are in the direction of X, and this y, global y, these are the displacements in the global coordinate system, D1, D2, and similarly D3 and D4. So D1, D2, D3, D4, these are the displacements at the joints of the member in the global coordinate system. And DM1, which is along the axis of this member, M is for the member, displacement in the member axis along direction 1 now. So these are the displacements in the local coordinate system, DM1, DM2, DM3, and DM4. What will be the order of, we are finding out in the local coordinate system, what will be the order of the stiffness matrix? It is going to be 4 cross 4. Why 4 cross 4? Why not 3 cross 3? 4 cross 4 because the kinematic indeterminacy of this element is 4. DM1, 2, 3, and 4. And same is the case for D1, D2, D3, and D4, which is the global coordinate system. Now, what will we do now to generate or to compute these stiffness matrices? What we do, we give displacement, unit displacement in a specific direction, and we restrain rest of the displacements in the structure. This was the basic concept. So what will we do now? We are generating now in local coordinate system the stiffness matrix. So what will we do? DM2 we will restrain, DM3 and 4 we will restrain, and we will give only displacement in the DM1 direction at this joint J now. And how that is possible? If we provide a roller here and if we start pushing it now, let's along this arrow, a unit displacement will be given. And as a result, what we do now, the definition of the stiffness matrix is what? Force required to produce unit displacement. So we, as a result of this unit displacement, what we do, we find out the force now, and that force will give you the elements of the stiffness coefficient matrix. Now, along this DM1 delta is equal to 1, when we provide, we will find out now S11, which will be along this DM1 and due to this DM1. Then along this DM2 due to 1 now, that will become our S21. Similarly, corresponding to this DM3, the action produced, that will become S31, and here it will become S41. So you can see all these 4 elements here. So this way we complete the first column of the stiffness coefficient matrix. When the first column is computed, what we do next, we keep this DM2 is equal to 1, and rest of these DMs we restrain them, we lock them. And that way everything will be now, every action will be produced because of this 2 now, DM2 now. Delta is equal to 1 when we put. So here it will become S12, S22, S32, and S42, and all these 4 elements are recorded here as a second column of the stiffness coefficient matrix. Then we now put DM3 is equal to 1, and rest we lock. So that way we generate the S13, S23, S33, S43, which are here, third column, and similarly when we keep this DM4 is equal to 1, so that way we can generate the fourth column of the stiffness coefficient matrix. So this is how the stiffness coefficient matrix and regarding the local axis is generated, in local axis system is generated. Next now, here now you see DM1, DM2, DM3, and DM4, and this is our positive axis. Now you can see the arrow, this is positive axis, and this is positive y-axis in the local coordinate system. So let's discuss this now, how we generate this. First we will discuss this, and then we go and generate a stiffness matrix in the global coordinate system. So turn by turn, we will start now. DM1 is equal to 1, then DM2 is equal to 1, then DM3 is equal to 1, and then DM4 is equal to 1. So here now, DM1 is equal to 1 is shown here. You see in that DM1 direction, a unit displacement is given. When this displacement, look, original length, the rest of the locations now you can see when we provide this roller, it means it cannot move now perpendicular to this surface now. It can move only in this direction. At the far end, we need to keep DM3 and DM4 is equal to 0. So what is the solution when we provide a hinge there? It means it can offer resistance in this perpendicular direction and along the length of the member also. So this is now the configuration where we can provide DM1 is equal to 1. Now, the original length was starting from here to the hinge now, but when we roll it down, now the length is less than the original one. When it will be shortened, when we provide a compressive force. So this is how we fix the direction of the force now. This is the action produced now, or the action required to produce this unit displacement. So means it will be in compression. Now, how we find out its magnitude now, how much action is required to produce this unit displacement. So it's a well-established equation now, delta is equal to PL divided by AE. This is how displacement is related when an axial force is applied to an element, PL divided by AE. But now delta is equal to 1. So when we put this 1 and when we reorganize this, so the force produced or the force required will become equal to L divided by AE. And this P will be the stiffness coefficient. Why this is the stiffness coefficient? Because this is the force required to produce this unit displacement. And that is the basic definition of the stiffness matrix. So the stiffness coefficient. So now this EA over L, this is the force produced here, and it is in the direction of dm1. So its designation now will become equal to S11. In the direction of dm2, no force is generated in that direction. So S21 is equal to 0. S31, it will be balancing this S11 now, EA or L, so it is in the opposite direction. And now S41 in the direction of DM4, we don't have any action now produced in this case, so that is equal to 0. So now we record its values. S11, it will become positive. Why? Because it is in the assumed positive direction. 21 is equal to 0, so that value is recorded here. S31, why this is negative now? Because the assumed direction was in the upward direction, but now it is in the opposite direction. DM3 was in the opposite direction, so because of that opposite direction, it is minus EA divided by L. And S41 is equal to 0. So that easily we can generate this first column of the stiffness coefficient matrix. Second, now what we do along dm2, we give delta is equal to 1, which is shown here. Now the weight of this element, it is equal to 0, and it's a pin here. So you take example of now weightless material in which you want to now give a rotation. So it means in this direction the force required will be equal to 0. Why? Because the weight of this we already assume is equal to 0. This along the axis, this force produced will be also equal to 0. And to put this system in equilibrium, these forces will be also equal to 0. So now S at 1 due to 2, S at 2 due to 2, S in 3 direction due to 2, and S in 4 direction due to 2, all these are equal to 0. And we record all these values. So the second column as a whole is becoming equal to 0. Next, now DM3, along the DM3 we are giving now, this was the original and we are stretching it by delta is equal to 1 now. Stretching means tensile force. So tensile force we are showing away from the joint. Now the designation of the actions produced, DM1, along the DM1 it will become S1 due to 3, S2 due to 3, S3 due to 3, and S4 due to 3 here. Again, PL or AE, we can use that equation, and this will become EA or L, S13. S13 will become equal to EA or L. Now, when we put this in the matrix form, it should be with appropriate signs also. Here, S13, if we look at it, is opposite to the direction of DM1. So this will become negative now. So this becomes minus EA or L. S23 is 0. S33, it is plus EA or L. Why? Because this is in the direction of DM3. And S43 is equal to 0. Now, along the DM4, we put delta is equal to 1. Again, the same, this element weight is 0. So when we start pushing it in this direction, no force will be generated. Axial forces are going to be equal to 0. So S14, 24, 34, and 44, all these values are going to be equal to 0. And we record those values as the fourth column of the stiffness coefficient matrix. And here you see this is DM4 is equal to 1 where we are applying. So finally, what we do, all the elements are now computed. So we put this stiffness matrix in this matrix form. EA or L, you can see it is common, so we can take it out, come outside this parenthesis. So this will become EA over L, and here we have 1, 0, minus 1, 0. The second column is 0. Third, we have minus 1, 0, 1, 0, and then fourth column is 0. So it is looking a very simple now matrix now if we take out this EA or L column. And this is the local stiffness matrix. This is the stiffness matrix. Here you can see computation of stiffness matrix as in the member or in local coordinate system. So this is the configuration of a pin jointed element. Now, in global coordinate system, it will be a bit complicated now, but it will depend on the simple now concept of the geometry. So which I'll be explaining now in the next slide. Here now we see now an element, and what we will do, instead of the local coordinate system, we will be giving displacement in the global coordinate system. And the global displacements are shown here along the x-axis at joint J. It is D1, then D2, D3, and D4. These are the displacements at K now. Now you should be able to visualize when we give displacement in the D1 direction, what will happen? If you start pushing this in the D1 direction, so what will happen? The member will start now coming in compression. Why? Because here at K it is hinged now and it's a surface now adjacent to this. So when you start pushing it to the right, what will happen? Shortening is going to happen now in this element. Why? You take the example of when you drag it, let's say it is coming under this joint K. So this vertical distance is less than this diagonal one. Why it is less? Because shortening has occurred in this member 7. This vertical is less than this diagonal. So when we get shortening, shortening is always because of the compressive forces. So this is how by the time we start pushing it to the right, it means we are inducing compressive forces in this member 7. If you start now, we'll discuss this at joint K now, but for now, you should understand that how we now put or how we assume now the direction of the force induced when we start giving it displacement in the right direction. It will be compressive. Compression means towards the joint, and from here also towards the joint. Now, to develop this stiffness matrix in global coordinate system, the procedure will be the same now. Turn by turn, we will start giving D1, D2, D3, and D4 is equal to 1. And we will find out the corresponding member and actions in this D1, D2, D3, D4 directions. So here now, along the now D1 direction, if you see, this was originally joint J and we displaced it to delta is equal to 1. So it is coming to this right roller location. And this green one now you see, this is becoming the length of this member. And obviously you can see this green length is less than this red one, which was the original. Means this member, by this sliding activity, it is coming in compression. How we find out how much is the change in length now because of this delta 1 is equal to 1 activity. We can draw from this green a perpendicular on this red one, and here we see that change in length now. This is the change in length. So it got reduced by delta L now. This is making an angle theta with the horizontal. Now horizontal distance, this horizontal we know it is equal to delta is equal to 1 because we are interested in the stiffness matrix, and stiffness coefficient element is calculated when we give a unit displacement. So these are the actions produced due to this unit displacement. D1 is equal to 1 we are applying. This P, we can very easily find out now how much is going to be the force induced in this member. Once we find out this P, when we resolve this along the horizontal and vertical components, so horizontal component it is corresponding to D1, vertical component is corresponding to D2. Here again, horizontal is corresponding. This we need to change. This is 3-1 and this is 4-1 now. This is slight mistake. So here, this is 3 because this is corresponding to 3 direction and this is corresponding to 4. Now, this is the right notation. So first what we do now, we find out the force produced in this member, which is along the length of this member, and then we resolve this into horizontal and vertical components, and that way we can find out the stiffness coefficient value. Now, when this theta is given, so what we can do now, we can relate this in terms of these trigonometric functions now. For instance, if this is theta, so this adjacent side, it will become its base, and this will become the perpendicular. And here this will become the hypotenuse. So if I want to use a relation to this delta L is known and this delta is also known. So what we can do now, we can find out a trigonometric function to relate these quantities, and which one is the appropriate function? It is cosine theta now. Why cosine theta in this case will become delta L divided by 1 now. So on next slide, and here you can see now S11, S21, S31, S41. These are now the member end actions which are corresponding to the member end displacements. And we are after these values now to find out the first column of the stiffness coefficient matrix. Now to find these now, first we need to find out this resultant force now, which is in this member 7. So P we need to find out first. So let's see how we can find this. Trigonometric function we discussed from the figure now, cos theta is equal to delta L divided by 1. Why 1? Because this delta was a unit displacement. So delta L divided by 1, this is now. Now our cos theta is equal to delta L. We don't want to write this one, it is already understood. And already we know that delta L is equal to PL divided by AE. This is displacement related to the axial force applied now. So if length is known, axial force is known, A is area, cross-sectional area of the member, and modulus of elasticity is known, we can find out the displacement produced. Now from this equation, what we have now, P is equal to how much force will be produced now? So it will be equal to EA divided by L times delta L now. And delta L we have, which is equal to cos theta. So instead of this delta L from here, this above equation, we put EA divided by L cos theta. Our cos theta already we know in terms of the coordinates that this is equal to xk minus xj. So this becomes xk minus xj divided by L. So now we can write this P, the force produced in the member, it is equal to EA over L. And instead of the cos theta, we put this in terms of the coordinates now. So it becomes xk minus xj divided by L. L times L will become L square. So finally, we have the member force produced is equal to EA over L square times xk minus xj. And actually, this member force is our AMD in member 7 because of the displacement in one direction. This is how we write the description of this AMD now, member end force. So this AMD will become, this is actually, meanwhile, we are generating our AMD matrix also, and its notation will be AMD. 7 is coming from the member number and 1 is coming from the region where we are giving the displacement. So now from this, now when we give a horizontal displacement at joint 1, now we produce S11, S21, 31, and 41, and similarly the AMD of the member number by this one displacement now. So that is produced. Now here now how we find out, we found this P now, the member force, which is equal to EA or L square times XK minus XJ, which is also equal to AMD 71 here. Now rest is now resolution of S11 will become equal to, here we have this theta now, so horizontal component of this will become equal to P cos theta. P already we have EA or L square times XK minus XJ, and cos theta we have, it is XK minus XJ divided by L. So when we multiply, we end up with this now, EA or L cube times XK minus XJ. The vertical component of this diagonal now, it will become equal to S2, and it will be P sine theta now, the vertical component, this one I'm talking about, which is shown here. So P sine theta, and it will be EA or L square XK minus XJ. This is the value of P from here, which we found in the previous slide. And sine theta is YK minus YJ divided by L. So here it is EA or L cube times XK minus XJ times YK minus YJ. L cube is coming from the product of this L square times L. If you look at the configuration is the same. Here it is EA over L cube, so this is also EA over L cube. This is the product of the horizontal coordinates, and this is the product of the horizontal and vertical coordinates. So again, product of the two things. Why here it is the product of the horizontal? Because here was action is in the horizontal direction and displacement given is also in the horizontal direction. Both are in horizontal direction. So this is why it is the product of horizontal coordinates. Only horizontal coordinates are involved. Here why it is the product of horizontal and vertical coordinates. Here if you see, action is in the y direction, but displacement was given in the horizontal direction. So that is why vertical and horizontal both are involved. So that is why both coordinates are involved, x and y. At the far end, we need to balance this S11 now with S31 now. Summation of fx is equal to 0. So here what is happening now? It is now opposite to the direction of that D3. So it is coming with minus sign now. So this is minus EA over L cube XK minus X. And here it will be balancing this one. So it means we need to reverse its direction. It should be looking downward now, or this negative is taking care of that answer. So this should be downward. Y in summation of Fy is equal to 0. So it should be balancing this form. So it is minus EA or L cube XK minus XJ times YK minus YJ. Now we'll be having discussion on this first now column. And maybe you cannot remember now this, but you need to find out analogy now in this case. The member force produced, it will be always with the EA over L square. And times the coordinates will be corresponding to the direction of the displacement now. Displacement was in the x direction, so x coordinates are involved now, and it is with the power 1. So now EA over L square, you will see when we go to the by providing the other displacements, you will see again it will be EA or L square, or only this coordinate will be changing. But this coordinate, which one will be involved, it will depend on the kind of displacement. Now, if displacement is in the horizontal direction, so it will be involving horizontal coordinates. This is about the member force from where we generate these A and B's. About the stiffness coefficient elements, if you see it was EA over L square, so this becomes EA over L cube now. And the coordinates involved now, F action and displacement given both are in the horizontal direction, so it will involve only horizontal components. F action and displacement both are in the y direction, so it will involve the product of the y direction. Now, F horizontal and action is horizontal and displacement given is vertical, so it will involve both x and y coordinates. So that will become, and you can see now the similarity. EA over L cube, it will be in the stiffness coefficient matrix, and it will be the product of the similar coordinates or the product of the different coordinate system. The different will depend. If action is in the different direction, then that the displacement given, so both coordinates will be involved. One. Now, second, now at the near end, if you see, S11 and S21 values are positive. So at the near end, these coefficients will be positive, and at the far end, they will be negative. So you can see here, negative and negative. So now we have generated the member force AMD matrix element here, I should say, and then the stiffness coefficient elements also. We go to the next step now. D2 is equal to 1 we will provide. So this is now the configuration where corresponding to D2 in vertical direction we are sliding, we are rolling it in the upward direction. This is delta is equal to 1 now. And this is angle theta. Here at joint J, this is angle theta with the horizontal. If this is angle theta, so it means this will be also angle theta. How? If this is theta, so means this angle which is now perpendicular, so this will become 90 minus theta. This angle is already 90, so 90 plus 90 minus theta and 180 minus that, it will give you this theta. So this is coming equal to theta now by using those calculations. What we are doing, again, we are finding out the member force fluids. Now what is happening again when we start sliding it on the upward direction, the green length, if you see it, is shorter than the red one, which was the original one. So it means again compressive forces are inducing. Here you see the direction of the force induced by the time you start sliding. Now how we find out this P now, and how we resolve this into rectangular components. This is the whole thing now. Here you see when we start resolving this in this horizontal component and vertical component, they are shown here at the joint. At the far end, the balancing forces of these are shown. Now let's see how these are created now. Here now, if we apply the same concept, so this is now becoming our delta now. You see here we are drawing a perpendicular, and this is the difference now. This length is similar to this one, and this is the difference. This is delta L now. So we have the opposite to this angle. We have this direction. This is delta L, and we have this hypotenuse, which is delta is equal to 1. So it means here the trigonometric function, which is sine theta, it is going to work now. So delta L divided by 1, it will be equal to sine theta. And it is shown, well, you can apply that one. So sine theta, this delta L, sine theta is equal to delta L divided by 1 means sine theta is equal to delta L now. Again, you can apply the delta L is equal to PL divided by AE. we can put delta L is equal to sine theta, and sine theta is equal to yk minus yj divided by L here, which is here now. The same process you can repeat. So force produced in this member, which will be AMD 7 in 7 due to 2 now, it is now equal to EA over L square times YK minus YJ. Its horizontal component will become P cos theta. So EA over L cube YK minus YJ times YK minus YJ. Why both coordinates are involved? Because action is in the one direction, which is horizontal, and displacement is given in the Y direction, which is 2. So 2 is vertical and 1 is horizontal. Both directions are involved. So that is why the combination of X and Y coordinates. EA over L cube, again, you can see this is the typical property of this stiffness coefficient element. Here now the vertical component will become P sine theta. So P is already, we know, EA over L square YK minus YJ, and sine theta is again YK minus YJ. So EA over L cube YK minus YJ square. Why only Y is involved? Because the action is in the vertical direction and displacement given is also in the vertical direction, and the same is here also. If we see 4 2, so again the action is in 4 direction, which is vertical, and displacement is given in the vertical direction, which is 2. So again only Y component is involved. Similarly here, if you see, action is in the horizontal direction and displacement given is in the vertical direction, so both X and Y's are involved. Again, you can see at the near end where displacements are given, so it's with positive value. This one is also with positive value, and at the far end, those are with the negative values. So this is how we find out the member force as well as the member end actions, which are the elements of the stiffness coefficient matrix. Second column is now produced. Third now corresponding to, here you see now D3. We are sliding it joint K to the right now. So this green is the new member now. Here now if you see, we see now increase in length, which is because of the tensile force. So here you see now P is shown away from the joint. Means this member is going to come in tension. And similar process we repeat for this one. First we find out the member force, which is given here, and then we find out the member and actions, which are the elements of the stiffness coefficient matrix. So here this designation will become now S13, S23. Here we have this S33, and this is S43 now. Again, at the near end, if you see, this value should be positive. This should not be negative. This is positive. Positive means we are not showing this. And this value is also. This is also, so at the near end, both now values are positive. At the far end also, you see both are negative now, the same concept. Again, now checking that EA or L cube is there for the stiffness coefficient. And xk minus xj, why x is only involved? Because the displacement given was in the horizontal direction and the action produced is also in the horizontal direction. Similarly here, if you see, the displacement given at 3 was in the horizontal direction, but the action produced is in the vertical direction. So horizontal and vertical both are involved. Similarly here you can see P, it's a tensile force now. So here it was P and this is also P now, EA over L square and xk minus xj, y horizontal displacement was given. Similarly now, when we give corresponding to D4 is equal to 1, again if you see from this green we are sliding it in the upward direction. So as a matter of fact, this should be red and this should be the new location we show with the help of the green line. Again, extension we see. Extension means because of the tensile force. This is how we fix the direction of the this tensile force. This is found out. We have this theta, delta L, and 1, so we can apply the trigonometric function, and then delta L is equal to PL or AE. We can find out this member force. Then we can resolve this into horizontal and vertical components, which will be giving us the stiffness coefficient values. So here we see now S14 in this direction. This is S24. This is S34, and this is S44 now. And you can see the configuration and all these things. So you should be able now to generate these values. Finally, now we are coming now and we are writing this in the matrix notation format. So EA or L cube was common, as we said, so we take this out common, and these are the coordinates now. We can write this in a simple form in terms of the trigonometric function. And if you see here, if we bring in now divided by L square here, so we see a nice trigonometric function relation now. Xk minus xj divided by L whole square will become equal to cos square. And that is recorded here. When we now bring in this L square, so this will become EA over L. So EA over L is shown here. This will become cos square. This xk minus xj divided by L times yk minus yj divided by L. This will become cos theta times sine theta. So cos theta sine theta. This is minus cos square. This is minus cos theta sine theta. Here now you see the trick. This stiffness coefficient matrix in terms of the trigonometric functions. Here, if you see. Here we have a slight mistake now. This thing, actually this element, here this one shown, this should be cos square theta. Here it is cos square. And this, actually this should be replaced with this one. And this is, when this is coming down, so this is becoming cos. So slight mistake, you can make this as a correction. Sin theta and cos theta. Because of this reason, we are now converting this matrix to this one. So this is just reorganization of this matrix. Now, look at the configuration now. Cos square, sin square, cos square, sin square on the main diagonal. Now, S21 is equal to S12 cos sin cos sin. S31 is equal to S13. So again, you see now, it's a symmetric matrix. It is a square matrix and it is a positive definite one. So if you remember the logo, this lower triangle, it means you can produce the upper triangle also. This is how the stiffness coefficient matrix in the global coordinate system will be. Now it is 9:27. So should we take a quick break now? And after the break, remember, we will continue maybe for a while and then we will start the YOC also. And remember, I'll be leaving at 11 o'clock. Right? So 1 hour. Sajjad, should we take? But it is going to be a short break.
Okay, sir.
ठीक है ना? So it is now 9:20. What is the time now, Sajjad?
9:27.
It's 9:27. So you should be back now by 9:40. 9:40 पे इंशाल्लाह हम मिलेंगे.
Okay, sir.
Is there any question? You can ask me question also if you have any confusion or if you need any clarity. So you are most welcome to ask.